All right. Hello, everyone. Welcome to the wolfSSL live webinar, Benchmarking with wolfSSL, presented by engineer Jacob Barthelme. My name is Jiyeon Park, and I will be moderating the webinar. So if we go to the next slide, just before we get started, I'd like to mention that wolfSSL will be at Black Hat's virtual event next week. Go to the website to register for a free business hall pass and come talk to wolfSSL during the event. So just to note, for this webinar, all attendees will be in listen-only mode. If you have questions, please use the Q&A box or raise your hand to be unmuted if you'd like to ask the question live during the Q&A session. We will host the Q&A session following the presentation. The webinar will also be recorded and is made available on our YouTube channel shortly after the presentation. I also invite you to follow us on Twitter at wolfSSL as well as our other socials. And feel free to email us if you have any questions or comments at facts@wolfSSL.com. And so now I'd like to give a brief company overview before we move to the technical presentation. So wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source, dual licensed embedded SSL library available. So OpenSSL existed at that time, but there was a demand for an alternative that was more easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and more modern API, and offered commercial style developer support. So wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections, and we have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of nearly 40 employees in 2020, most of which are engineers. This progress is, of course, supported by our strong partner network that we're very proud of, which includes Microsoft Azure, Broadcom, and Curl, just to name a few. So since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and a FIPS-ready offering, MQTT up to version 5 specification, SSH version 2, TPM 2.0, and a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support. All of these offerings are accompanied by through maintenance and support plans up to the 24/7 level, and we also offer full service consulting. So with all that being said, I'd now like to turn it over to Jacob to talk about benchmarking.
Thank you, Julia. Today I'll be covering many benchmark items with wolfSSL, starting with the history of performance with wolfSSL, how to collect benchmarks using the bundled application that comes with wolfSSL, some of the hardware crypto acceleration available for use with wolfSSL, TLS benchmarks, and some enterprise applications with asynchronous crypto along with program language wrappers. There are multiple reasons to want increased performance with cryptography. When running on resource-constrained devices, the option to offload crypto operations to the hardware can reduce memory size. One case of memory reduction is often seen with offloading the memory of the AES tables to the device. Increase in performance is also useful for non-resource constrained devices that want to keep a responsive user interface. Decreasing the time it takes for a crypto operation to complete will decrease the wait time that a user experiences. Faster crypto operations are also helpful in cases where real-time responses are required. An example of where a real-time response would be required is when applying the brakes on a vehicle. You want any authentication of the command to brake in an emergency situation to be as close to zero as possible. New hardware acceleration support is constantly being added to wolfSSL. This shows some notable additions and when they happened, but it is not a full or comprehensive list of all of the hardware accelerations that we support. Each of these mark the initial addition, but do not show the times for when updates and additions of algorithms were done. Some of the first hardware accelerations to be added to the library were the MMCAU back in 2012. which was known then as Freescale, but since has become NXP. Then STM32 hardware support was added later in 2013. It started with the STM32 F2 series, and we later added in the F4 and F7 series support. For the library's name change in 2015, there was also the addition of Renesas hardware, Intel AES-NI, and PIC32MZ support. After the name change to wolfSSL in 2015, support for hardware acceleration for TIC boards was added in a notable amount of Intel assembly additions. In 2016, an initial edition of ARMv8 crypto extensions was added to wolfSSL, speeding up AES operations and SHA-256 operations. In 2017, a massive increase in performance was added for public key operations. This was with the addition of single precision builds with wolfSSL version 3.12.2. And a couple of more recent hardware accelerations in the last couple of years was the addition of CryptoCell, Renesas, and Xilinx Panalytics. There are common metrics used when collecting performance values. The most common for symmetric key operations is megabytes per second. This is the number of megabytes of data that can be encrypted, decrypted, or hashed in 1 second. Another common metric used is cycles per byte. This is the number of CPU cycles it takes to process a byte of data for encryption or decryption. With public key algorithms, it is common to use operations per second. The number of operations that can be performed in a single second. It's also common to use an average time for each of the public key operations. With TLS, the common metric used is time per connection, how long it takes for the TLS handshake to finish, and throughput, how fast data can be pushed through an established TLS connection. The next couple of slides I have will be going over the benchmark application bundled with wolfSSL and some of the performance optimization options when building wolfSSL. In each release of wolfSSL, there is a benchmark application bundled along with it. This application is located in the directory wolfCrypt benchmark and is named benchmark. When building with AutoTools, this application is built by default. The application has been expanded upon since it was first introduced. Recent versions of the application include Japanese translations and options for running specific algorithms only rather than having to run all of the algorithms each time. There is also a CSV flag. This prints out the benchmark results in the comma-separated version so that it can be easily copied and pasted into spreadsheets. A full list of the options can be seen by using the -H flag. In cases where AutoTools is not used, benchmarks can be collected by calling the function benchmark test and including the header file wolfCrypt benchmark benchmark.h. With AutoTools not creating the application, the source file benchmark.c located in the same directory also would need to be compiled. Sometimes when running on resource constrained devices, it can be better to use smaller buffers and lower number of runs when collecting benchmarks. So we have the macro bench_embedded to set up the benchmark runs for using a more resource constrained and embedded friendly benchmark. This here is an example of running the benchmark application from a desktop terminal. It's with a basic, just configure, then make, and then you run wolfCrypt benchmark from the root wolfSSL directory. Often to build wolfSSL for hardware acceleration, an enable flag or macro define is needed. An example would be with enabling Intel assembly by using --enable -Intel Asm, or by enabling SP builds with enable SP to turn on the single precision performance. One other option for ECC acceleration that is in wolfSSL is the define for macro FP_ECC. This increases memory usage some, but it caches ECC points for speeding up ECC operations with keys that are used multiple times in a row. By default, the hardware accelerations are not enabled. The default build is set for portability and security, having side channel attack resistance turned on. A significant public key performance increase that I mentioned a couple of times previously was added into wolfSSL by the senior software developer, Sean Parkinson. The single precision code is optimized for commonly used key sizes. The algorithms and key sizes are with ECC NIST P256, 384, along with 2048-bit, 3072-bit, and 4096-bit keys with RSA and DH. There's a slight increase in code size when this feature is turned on, but a significant gain in performance. It can be, this slight increase in size can be offset if you know that you're only going to be doing NIST P256, for example. You can disable building some of the other options in wolfSSL where it's very modular. You can turn off other features to help offset the increase in size. It also supports ECC key generation and shared secret creation with ECC. When using auto tools, this all can be turned on by using the enable flag, enable-SP. Okay, since the initial C software version of SP, there has been additional optimizations for specific hardware. Turning on the optimized assembly builds can be done by using the enable flag SP-ASM. And currently versions have been written for Intel, ARM, and Cortex-M processors with our single precision build. When not building with auto tools, macros can be used to turn on the single precision build. There's macros for each of the algorithms supported, RSA, DH, and ECC, and macros for a slightly smaller build with wolfSSL_SP_small, and macros for hardware-specific speedups. The next several slides have performance values collected with hardware acceleration turned on, starting with some of the embedded devices and ending with some desktop use cases. There's hardware acceleration support, as mentioned before, for the STM32 devices. Some examples of them being the STM32 F2, 4, and 7 series. And recent additions have been made to increase the performance with STM32 devices. The AES operations on the STM32 F777 device increased by over 8 times, and the SHA-256 operations double in speed once these hardware accelerations have been turned on. With SP flags used during the build of wolfSSL, the public key operations are also greatly increased. On the left here, I have the symmetric key operations, and then on the right here is the public key operations, comparing software operations per second versus accelerated operations per second once SP has been used. Two of the Renesas boards that are supported with wolfSSL are the Renesas RX65N and DKS7G2. On both devices, AES and SHA-256 are sped up, and the table on the right also has the increase with SP and our Cortex-M assembly additions to the SP. The wide range of NXP devices are supported with wolfSSL. There's also examples of building with these devices in Code Warrior projects in the wolfSSL IDE directory to get started with them quickly. The most recent NXP device tested on was the K82, and we saw a great increase in AES and SHA operations when turning on the hardware acceleration with that. Since this is an ARM device, it would also support some of the SP builds, but I just have in this table here showing off the hardware acceleration that the K82 has with the AES and SHA-256. Some of the other devices supported by wolfSSL are the Coldfire boards, Cavium, Microchip P32, Nordic NR F51, Atmel ATE CC508A, NXP LTC, and we have support for the NXP CAM. There's more in addition to this that we have up on our website. Just too many to list in one spot here. A lot of hardware acceleration support has been added for ARM devices. This includes the early editions of the TFM assembly speedups, which are just small speedups for the math library to use ARM assembly. Support for the ARM v8 crypto extensions to be used with AES and SHA-256 operations. Neon instructions to speed up vector operations when performing SHA-20 and Poly 1305. And assembly optimizations additions that were added to the SP for RSA, ECC, and DH operations. The crypto extension support and Neon with SHA-20 Poly 1305 can be turned on when using AutoTools by using the enable flag ARM ASM. And to enable the assembly speedups with the SP flag, you would add SP-ASM. To showcase the ARM hardware acceleration, some benchmark values were collected on a Heike LeMaker board, which runs at around 1200 megahertz. The table on the right shows the operations per second with and without using the assembly optimized version of SP. You can see that ECC and RSA are more than 10 times the number of operations completed per second once the hardware acceleration is turned on. And the table on the left just gives a visual comparison about how much faster it is with the hardware acceleration turned on. This slide demonstrates how much of an improvement in performance the ARM v8 crypto extensions and Neon instructions make. All of the AES and SHA-256 operations make use of the crypto extensions, and again, the SHA-20 and Poly 1305 are using the Neon instructions. Another one of the major chipsets supported with wolfSSL is Intel. wolfSSL's initial hardware acceleration with Intel was the addition of AES and I to speed up AES crypto operations. This can be enabled with the enable flag AES and I. When using AutoTools, later on RD-RAND and RD-SEED was added along with some additional assembly instructions. To make it easy for enabling all of the supported Intel assembly speedups at once, the enable flag enable Intel ASM was added. The AVX instructions are used to speed up SHA-220 Poly-1305. It's similar to how we did the speedups with the Neon instructions in the previous ARM slides. The AVX instructions are also being used though to speed up Curve 25519, SHA-256, SHA-512, and to speed up the SP code. It makes it a good enable option to have selected when using the new TLS 1.3 cipher suites. These benchmark numbers were collected on a Mac laptop using a quad-core i7. The values show the difference between building wolfSSL to use software only and building wolfSSL to use SP with assembly optimizations. You can get well over 3 times as many RSA and ECC operations completed in 1 second when using optimizations versus when using software only. And on the left here, I just pulled out the RSA. I got a typo there. It's supposed to be 2048 public key operations, and showing the comparison between the two, just for visualization. There's a similar spike in symmetric key performance with the AES&I and AVX instructions being used. Next, we'll be going over the TLS benchmarks. To measure TLS performance, there are a couple of bundled options that come with wolfSSL. One option is to run the script located in scripts benchmark, located at scripts benchmark.test. The script takes in arguments for measuring time per connection or throughput and the number of connections to perform. If wanting to compare all cipher suites performance, the application located at examples benchmark called TLS_benchmark could be ran. It will go through and collect both throughput and average connection time for each of the cipher suites. Alternatively, the example client and server can be used with arguments passed into benchmark connections. The capital B option can be used to collect throughput, and the lowercase b option on the client side can be used to benchmark the number of connections. The most recent addition to TLS is the TLS 1.3 protocol. This version cleaned up a lot of the handshake and made it more efficient. The reduction of round trips helps speed up the handshake a little. As can be seen by the slight improvements to performance listed here, where you get like a 15% improvement in the performance with ephemeral DH and with RSA handshakes. Most of what I've gone through so far is geared towards embedded devices or simple desktop applications. The next couple of slides go through use cases at more of an enterprise level involving the asynchronous crypto with Intel Quick Assist and benchmarks of our JSSE implementation. Asynchronous crypto is often used in more of an enterprise situation where massive amounts of sign and verify operations are taking place. This could be something like an Apple server farm that is handling millions of TLS connections regularly. It is a feature that allows for operations to not block till completion and for an increase in operations happening in parallel. The two main hardware platforms out there for this are the Intel's Quick Assist and the Cavium Metros, and both are supported by wolfSSL. To enable asynchronous cryptography, the enable flag async crypt is used. with the default bundle, this enable option will give a warning just because the code for Asynchronous Crypto is an add-on feature that we have that does not come bundled with the open source wolfSSL package. The next slide shows the performance of Asynchronous Crypto ran on an Intel i7 with Quick Assist version 1.7. Where the Asynchronous Crypto really performs well is with the public key operations, which make up the bulk of the time during TLS handshakes. With AES operations, it can sometimes be slower. Well, it is slower than just like the AES-NI on the Intel chip. So sometimes it can be beneficial to just be using the Intel AES-NI instructions. wolfSSL has multiple language wrappers that come bundled with the open source package, including our C# wrapper, our Python wrapper, and our Java JNI wrappers. There is a separate repo on GitHub for the wolfSSL JNI that has a full JSSE implementation to be used with Java projects. That includes steps to be able to replace it as the default provider in an Android device. The wrapper is still called down to the C library and can leverage the existing hardware acceleration. Below is a table showing the comparison of the default Sun JSSE provider versus the wolfSSL JSSE implementation. Our hardware accelerated build is almost 5 milliseconds faster than the default Sun JSSE provider on Mac OS. You can also see there is a slight performance hit for adding on the wrapper, about an increase of 1 millisecond over what the default C client is. So the default C client without the wrapper is 9.694 milliseconds in average time. No acceleration. And then the default software-only client with JSSE is at the 10.92 milliseconds for an average connection time. But the default Sun JSSE is all the way up to at 13.34 milliseconds as an average connection time. This just gives a visualization with the Sun JSSE provider being on the far right. Wolf JSSE here. So wolfSSL is constantly adding in hardware acceleration. If you have a device that has hardware acceleration that is currently not supported in wolfSSL, feel free to contact us. Some more of our benchmark values can be found up on the main wolfSSL website. This is just basically the tip of the iceberg that goes over a lot of the common benchmarking and how to perform benchmarks yourself with wolfSSL using the crypto benchmark application.
Thank you so much, everyone, for joining this webinar, and a special thanks to Jacob for leading us on today's topic. Again, as I said, the webinar will be recorded and made available on the YouTube channel. And again, I invite you guys to follow us on our Twitter at wolfSSL, as well as our other socials. Thank you so much for coming, and I hope you all have a great rest of your day.